Well, hello, Hans Birger. Anyway, it's great to be here for your birthday, and in the short time that I had to prepare it, I decided to prepare a talk on information and communications technology and the future of mathematics teaching. And my name is John Perham. I'm from the School of Mathematics and Statistics at the University of New South Wales in Sydney, Australia. So let's start. Let's start with Hans Birger. Well, my first meeting with Hans Birger was when we appointed him as a temporary lecturer in the Institute of Mathematics at the University of Odense around 1976. At that point, the main purpose of the university's science faculty was to support the education of medical doctors in the medical faculty and to produce teachers for local high schools. Gymnasia. This was not an ideal situation for a new professor of applied mathematics, but having Hans Birger as a colleague was one of the few bright points. Since then, modern information and communications technology has transformed the university, so it is now the University of Southern Denmark, the second largest university in Denmark, with all the faculties of a modern American university, including the Faculty of Engineering. It is fair to say that all these developments have been driven by modern ICT, including a vigorous interaction of the university with many of the large industrial concerns in Denmark, including AP Møller, Grundfos, Danfoss, Lego and Novo Nordisk. Well, Hans Birger left the university after a year and disappeared until he sent me an email about 3 weeks ago. I can see from the website that he is much loved by the Institute in Bergen for his contribution to excellence in mathematics teaching, which is also the topic which has most interested me over the last 15 years or so. Before getting on to the technical part of this talk, let me congratulate Hans Birger on achieving his 70th birthday. I think it is wonderful that his colleagues have decided to celebrate it in this way, and I'm very happy to take part in the celebrations. Anyway, to illustrate the concepts, I will use the most complicated calculation carried out by normal citizens, namely the discharge of a mortgage. So let's start. So ICT in mathematics. Well, I find it strange that despite the involvement of mathematicians in the development of computers and computer science, it's distressing to see how little ICT is used in formal mathematics instruction. This should be compared to the very large number of informal presentations available in sites like YouTube, where I've also placed a number of videos related to my teaching and research, including this one. For example, modern computers were designed by mathematicians such as John von Neumann and Alan Turing. The first real computer was built in 1948 at the University of Manchester by the mathematicians and engineers from the legendary code-breaking group at Bletchley Park. At UNSW, where I still teach first and second year maths tutorials to students of engineering, we're encouraged to use blackboard and chalk. Because there are over 2,000 students of our standard first year course, multiple lecturers still hold the lectures because there's no lecture theatre which can hold that many students. However, there is a little group of us encouraging the upload of lectures onto YouTube and also presenting the standard solutions to some of the tutorial problems. Well, one of the earliest areas in artificial intelligence were attempts to automate mathematical proofs. The computer algebra system Reduce was first issued in 1970 and with version 3 produced in 1983. I used it then to carry out complex algebra for describing perturbation theories for the thermodynamics of small molecules. In more modern times, many users of computers employ computer algebra systems such as Maple and Mathematica to manipulate complex formulas. My earliest application of ICT in teaching was using the spreadsheet program SuperCalc 3 in an optional computer literature or literary course. I don't know what this thing is. It keeps going, but I can get rid of it. literacy course at the University of Odense back in the mid-80s. An aspect of the way it organises data and formulas led me to get relatively weak mathematics students to carry out fairly complex mathematical calculations. This is because a cell, the fundamental concept of a spreadsheet or spreadsheets, can contain a formula expressing a value from the values of other cells. The dual natures of formulas and values lies at the heart of mathematics. The example I've chosen to illustrate how these pieces of software can contribute to understanding relatively complex mathematics is the problem of calculating the monthly payment to reduce a mortgage to zero after a certain number of years at a given fixed rate of compound interest. Well, so let's get going on the problem. So let us start by inputting the data that we need to simulate a mortgage. So let us remind ourselves of the inputs. Assuming that the interest rate does not change, in other words, a so-called fixed rate mortgage, we need to enter it in percent using this. And this, by the way, is a piece of software called Mathematica. And this means that the name rate here is associated with the value 5. And we can see that using this here. Now, usually the interest is compounded monthly, so we will have to insert the number of periods in a year using this, and that's usually 12, so we'll do that. And the number of years of the mortgage is also predetermined, so we can set its value using years, 20 years. And the amount we wish to borrow, or the balance we need to enter using that, equals B, and then we can give a numerical value to B using this. Well, anyway, what's the interest? Well, in the first period it could be calculated as the rate in percent divided by 100, and then divide that by the number of periods, and then multiply that by the balance. And we can do that using this. And so this tells us in the first period we're going to have to pay some 416 units, kroner or dollars or whatever you like. And what we need to do now is to calculate the monthly repayment such that at the end of the mortgage, after 20 years, the balance is zero. And there are two ways to do this. Well, a lot of ways of doing it. We can use numbers, as we can see in the Excel file, or using computer algebra, which you can see here using the program Mathematica. So let's start with the spreadsheet. Well, this is a spreadsheet. This is Excel. We'll put that up here. So here I've entered the interest rate in this cell here, 5, the periods, the number of years, the amount of the loan, and here is my guess of the repayment per period. It's got to be greater than the interest, clearly. Anyway, so what have we got here? Well, at the start of the mortgage, the period is 0, and after the first period, that's 1. And it's interesting to see how this is done. This cell here is equal to 1 plus A11. So in other words, this becomes 1. And then if I copy this cell all the way down for the 240 periods, then I'll get the sequence of numbers 1 up to 240. Well, here's the first cell here, and that's got the balance, and you can see that's equal to E5, which is up here. So in other words, I do this by typing in equal, and then that. And now I have to calculate the interest in the first period, and I do that by taking the interest rate, E2, well, we'll do it, E2, and we want that to be, that number to stay fixed, and then we want to divide that, we've got to multiply it by the balance, and the balance is over here, and then we want to divide that by brackets 100 times the number of periods, and then we enter that, and that produces that number. So the repayment now has to be equal to this number here, which we need to make constant, minus this number here. And now we have to calculate the new balance, so that's equal to this balance minus the repayment. And now, this is clever now, we're going to copy these two cells down to here. If something hasn't worked here. And what hasn't worked is we forgot to make this a constant. So let's go and do that. So we edit, sorry, this one here. We edit that cell, and we now take this number here, which should be that, and we make it an absolute reference, and then we copy that down to here, or these two down here, and now it's working. And now all we have to do is to copy all these cells here down to the bottom of the table there, and there we have it. And now what's the final debt? That should be that. So the final debt is equal to something wrong here. So go down here. And there we have it. So now what we see is the final debt is negative, so this means that our monthly repayment is too big. So let's put that down to $600 and see what happens. Well, now we see that the final debt is $24,000, so that's not enough. So let's change that to $650. And now the final debt's much smaller, so it's still positive, so we want to change that. So let's do it a little bit. 660. and we can see that the final debt is small and negative. So we're almost there. So let's put that to 659. And we can see that it's much closer to 660. So we'll edit that. 0.9. And that's not quite enough. So we'll edit that again. And now the final debt's down to $2. So we'll change that a bit more. And we've got it now. So that's the solution to the problem. So we've found the debt here. So let's save that file and get rid of this. And now get our Mathematica back again. And let's start with that. So what are we going to do? Well, we can see that we've got this number, the rate divided by 100 divided by the periods. So we're going to call that R. And let's do that. So R is 1 over 240. And if we don't express the value of R, then that just stays as a variable. So the interest is R times B. And the repayment is the payment P less the interest, and then the new balance, which we'll call B1, becomes B minus that. Well, let's now do the second period. So the interest is now R times B1, and the repayment is P minus that, and the new balance, I'll explain what that means in a minute. The new balance is the old balance minus the repayment, and so that's that. And what I'm going to do is to develop that as a polynomial in this parameter R. Now, what can we say about this? Well, we can see that this function is linear in both the balance and the repayment, but it appears to be a quadratic polynomial for the balance and a linear function for the. So let's do another one. Now this section here is basically copied from this one here. So the interest is that, and the repayment is P minus that, and the balance is now this guy here, and we can see that this is a polynomial, and we're beginning to get a clue about the structure of the general expression, because if we look at the polynomial involving b, then we can get that by getting the coefficient of b in this expression here. We can see that that's equal to this cubic polynomial, and we can simplify that, and it's indeed 1 plus r cubed. So the coefficient of p can now be got, and well, what does that look like? Well, we're not quite sure. So let's do a fourth period. So the interest is now r times b3, and you see that these formulas get more and more complicated, and the repayment is p minus the interest, and the new balance, which we can calculate as a polynomial, looks like that. And let's dig out the coefficient of b. It's that, and we can simplify that using that. So in other words, what this leads us to believe, that in the nth period, then the coefficient of b will be 1 plus r to the nth. And now we can isolate the coefficient of p, and that's this thing here. And we can see if we multiply this by r and subtract 1, then what we'll get is this one here with a minus sign. So we'll simplify that, and that's true. So that the conclusion is that B4 is given by the coefficient of B times B plus the inverse of this, which is 1 plus this number here divided by R times P. That looks kind of neat, and we can check that that's correct by subtracting that balance from the original balance, and that number should of course be 0. And it is. So this looks like this is the formula. So now in mathematics, what you would then have to do is to do this by induction. So our postulate is that the nth b is b into 1 plus r to the nth plus p into 1 minus 1 plus r to the nth divided by r. So let's do that. And now calculate the nth period, the next period. So the interest is r bn, and the repayment can be calculated using that, and the new balance can be computed using that, and the coefficient of b can be, so this is the nth plus 1th balance, and that's 1 plus r to the 1 plus n, and the coefficient of p, and this is the same formula but with n replaced by n plus 1. So this amounts to a proof by induction that that is indeed the formula. So let's use that formula to compute the discharge of the mortgage. Well, if we look at this expression here, we can see that this involves is a linear function of b and p, which is what we want to find. So, and we want to find when that's 0 with respect to b. So that we can use the formula for the solution of a linear equation, and using that to get the value of p to discharge the mortgage, and we can then get the numerical value by taking that value, setting r equal to its numerical value, and setting n equal to the number of periods times the number of years, and then evaluating that with all the, and then finally taking the numerical value of that. So there we go, and there you are, 659.956, which is what we found from the spreadsheet. So so that's my example of how you can use computers to gain some understanding of the mathematics involved in simple but rather complicated real-life problems. So thank you. Well, hello, Hans Birger